Changes in the process location can lead to out-of-specification products. In this lesson, you will learn how to create a control chart for averages to monitor this process location. And hello again to this lesson, which essentially has 4 learning objectives. Of course, you should be able to name the essential basics of a mean chart. You should also be able to use a sample to calculate the mean and the spread in the form of the standard deviation. Certainly, the focus of this lesson is that you should be able to create a control chart yourself and calculate the warning and control limits. Finally, you should have a feeling for the relation of the warning and control limits to the specification limits of the characteristic. This lesson is divided into 3 chapters. In the first chapter, we get an overview of the different mean values and the essential elements of a control chart for mean values. In the second chapter, the actual control chart is created and the warning and control limits are calculated. In the last chapter, we compare the warning and control limits with the specification limits of the monitored characteristic. To be able to classify the average control chart in comparison to the other quality control charts, this picture shows the connection between the various characteristics and the control charts used. The different characteristics are shown on the left and the different control charts on the right. The quantitative characteristics shown on the left can be divided into 2 different categories. First, the variable characteristics. These are all characteristics that can be measured. They always have a value and a unit. Examples of this would be the length, hardness, weight, surface roughness, or tensile strength of a component. Second, there are the attributive characteristics. Those are all characteristics one can only count. But we don't want to go into detail about them here. On the right, we have the different control charts for variable characteristics with a white background. These are also called Shewhart charts, named after American Walter Andrew Shewhart. As you can see, there are 3 control charts for monitoring the process location and 2 control charts for monitoring the spread. The average chart is one of the location charts. Let's start with the basics of the average chart. As a practical example, we take this tried and tested piston again. The product characteristic to be monitored is the nominal diameter of 60.1 mm. When we talk about the mean, we mean the arithmetic mean. This is probably the most well-known mean and is calculated from the sum of all values divided by their number. There is also the median. This is also called the central value. It is the value in the middle of the values ordered by size. The mode is then shown on the far right. The mode is the most frequently occurring value. The limits for a control chart for the median are calculated differently than for the mean, so there is a separate lesson for that. As you may already know from the control chart for individual values, the main parameters of the control chart are also shown here in the header. Only the scaling of the y-axis is there for the mean values. In the lower part, the mean value was calculated for each random sample and entered in the table. The warning limits are calculated such that there is a 95% probability that the mean of a sample will fall between them. And the control limits are calculated such that there is a 99% chance that the mean of the sample will fall between them. The various formulas used to calculate the warning and control limits are shown on the left-hand side. In this lesson, we will only calculate the limits using the formulas on the right and take the factors AC and AW from corresponding tables. Let's briefly review the meaning of the symbols in the formulas. Mu is the population mean, and mu hat is the mean of a sample, which is used to estimate the true value of the population. Sigma is the standard deviation, and sigma hat is the sample standard deviation. AC and AW are factors for calculating the warning and control limits. How to calculate these factors yourself is explained in a separate lesson. The required quantile of the standardized normal distribution is also the subject of another lesson. To calculate the limits, the process location mu and the spread sigma of the population must be known. Since these are usually not known, they must be estimated as best as possible using a random sample. This random sample can be taken from an ongoing series production or from a pre-series carried out specifically for this purpose. In this chapter, let's take a look at the result of such a pre-series and use the measurement results to calculate the mean value and the spread. Several random samples were taken and the diameter of each part measured, and the measurement result was entered in the table. Then the mean value was calculated for a sample size of 5 and entered in the control chart. This resulted in the value curve shown here. In the calculations for the warning and control limits, it is assumed that the mean values are approximately normally distributed. A visualization in the histogram and the envelope curve above it should be sufficient proof of this at this point. The mean value was calculated from 5 individual values and written in the right-hand column. The grand mean value was in turn calculated from these mean values. The grand mean is the average of the means, recognizable in the symbol by the 2 dashes above the X. The grand mean has a value of 60.105 mm. The standard deviation now has to be calculated on the basis of the same measured values. This can be done, for example, with MS Excel and the function stdev.s. However, there are other methods that can be used to estimate the standard deviation. 2 of them are shown on the right. If you don't have a computer to help you, you can also calculate the standard deviation manually using the range R and the value dn. Values for dn or an would then have to be taken from tables again. And with that, we have everything we need to calculate the warning and control limits. The mean, mu, is 60.105 mm and the standard deviation is 0.03 mm. Both values were transferred to the header of the control chart. In this part, we now come to the calculation of the 95% warning limits and the 99% control limits. First of all, only the 2 formulas for calculating the upper warning and control limits are shown on the left-hand side. In this, mu is the mean and sigma is the standard deviation, which we calculated in the previous chapter. The only unknowns are the 2 factors AC and AW. These must be taken from tables. The factors AC and AW depend on the sample size and the confidence number. The table on the left shows some example values for different sample sizes and the non-interference probabilities of 95 and 99%. How to calculate these factors yourself will be explained in a separate lesson. For a sample size of 5, we take the value from the table as 0.877 for AW and 1.152 for AC. Both values were also entered in the header of the control chart. For the further calculations, the table on the left has been expanded to include the formulas for the lower warning and control limits. If you now enter the values in the formula and calculate the upper control limit, the result for UCL is 60.14. This upper control limit has already been drawn on the control chart. A value of 60.13 is calculated in the same way for the upper warning limit. The limit was also drawn on the control chart. And we get a value of 60.08 mm for the lower warning limit and a value of 60.07 for the lower control limit. Both limits can also be found in the control chart. But what do these limits mean? For the warning limits, this means that there is a 95% probability that the mean value calculated in each case will be within these limits. And with a 99% probability, the mean will be between the control limits. This means that the probability that a mean value is outside the control limits is less than 1%. If such an improbable event occurs, this is an indication that the process is out of control. The reason for this limit violation must be found and, if necessary, the process must be readjusted. In this last chapter, let's compare the specification limits for given process capabilities with the control limits. These are not really related to each other, so the comparison is only intended for a somewhat deeper understanding. As we have just seen, the calculation of the warning and control limits of a control chart does not require specification limits of the characteristic. These are based solely on the process parameters. This means the mean value of the measurement results and the spread of the process. When calculating the process capabilities, on the other hand, the specification limits of the characteristic must be taken into account. Usually, these already exist and are tailored to the function of the component or the product. Here, we choose the opposite approach and set the specification limits in such a way that a given process capability is met. The result has already been anticipated here in the dimensioning. So, now the formulas for the critical process capability on the left and the formulas below have been transposed so that the lower and upper specification limits can be calculated. Common critical process capability values are 1.33 and 1.67. If you want to know more about this, you should take a look at the corresponding lesson. If we now use the known values for the mean value, the standard deviation and the capability index 1.67, we get a value of 60.26 mm for the upper specification limit and a value of 59.96 mm for the lower one. Both limits were drawn on the control chart. Doing the same for the capability index of 1.33 gives an upper specification limit of 60.3 and a lower specification limit of 59.99. All mean values can be expected between the control limits with a probability of 99%. With a process capability of 1.33, all values are to be expected within the specification limits with a probability of 99.99%. With a process capability of 1.67, this is 99.999%. To say it again clearly, the warning and control limits were calculated on the basis of the process parameters, mean and standard deviation. Any specification limits were not taken into account. The specification limits come into play when machine or process capabilities are to be determined. A single measured value can exceed the control limits. This alone is not an indication of an out-of-control process. If the measurement is within the specification, then the measurement is okay. Only when the mean of a sample is outside the control limits is this an indication of a process that may be out of control. Such an average chart is therefore more robust against outliers than a chart for individual values. Well, that was a lot of new information. Therefore, I would like to conclude by repeating the 4 most important key messages. The non-interference probability for the control limits is 99%, but can also be 99.73%. This then is a width of 6 times the standard deviation. The control limits are determined on the basis of the process spread, process location, and the sample size. If a mean value is outside the control limits, the process must be readjusted. And, last but not least, average charts are more robust to outliers. If you found this lesson helpful, please let me know and leave a comment. Thank you for that, take care and see you next time. Bye!